Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Privacy by design is a principle that emphasizes embedding privacy protections directly into systems from the very beginning, rather than adding them as an afterthought. This proactive approach shifts the focus from reacting to problems once they occur to preventing those problems from arising in the first place. It is a widely recognized standard in modern data protection law, including the General Data Protection Regulation in Europe, and it forms the backbone of trustworthy artificial intelligence. For AI in particular, privacy by design is critical because the scale and sensitivity of data used in training and deployment make reactive strategies insufficient. Building privacy safeguards into the earliest stages of design ensures that systems can operate responsibly while maintaining user trust. The core principles of privacy by design revolve around minimizing harm and maximizing control for individuals. One major principle is data minimization. Collect only what is truly necessary and retain it only as long as needed. Transparency in processing is another, ensuring that users understand what happens to their data. Security by default requires systems to be configured with the highest reasonable safeguards, avoiding the assumption that users must opt in to protection. Finally, privacy by design respects autonomy by empowering individuals to make informed choices about their data. These principles provide a foundation for operationalizing privacy in practice, balancing the goals of innovation with the rights of users. Privacy by design also aligns closely with legal obligations across jurisdictions. The European Union's General Data Protection Regulation explicitly requires it, mandating measures like minimization, accountability, and purpose limitation. The California Consumer Privacy Act and related U.S. laws impose similar obligations, emphasizing transparency and user control. Sector-specific regulations, such as those covering healthcare or financial data, reinforce these expectations in high-stakes contexts. International recognition of privacy by design has grown, making it a global standard rather than a regional quirk. For organizations deploying AI, aligning with these frameworks is not just a matter of compliance, but also a signal of responsibility to stakeholders worldwide. One of the most concrete practices under privacy by design is minimization. In practice, this means collecting only the data that is strictly necessary for a given purpose. Retention without purpose is to be avoided, with clear rules defining how long data is kept and when it must be deleted. Sharing should be limited to essential parties, with contracts or safeguards ensuring appropriate use. Monitoring compliance is an ongoing task, as minimization can quickly erode if teams are not vigilant. For AI, where large datasets are often assumed to be inherently valuable, minimization requires deliberate discipline to prevent unnecessary collection that introduces both risk and liability. Closely related is the principle of purpose limitation. Every use of personal data should be tied to an explicit, clearly defined scope. Secondary exploitation, such as reusing a dataset collected for medical research to train unrelated commercial systems, violates this principle. Purpose limitation requires documentation of the justification for processing and mechanisms to enforce restrictions through technical safeguards. In AI pipelines, this might mean restricting access to subsets of data or embedding flags that prevent repurposing. Purpose limitation ensures that information is used in line with their expectations, reducing the risk of misuse or erosion of trust. Default settings are another cornerstone of privacy by design. The idea is simple but powerful. Systems should be configured with the strongest privacy protections enabled by default, rather than relying on users to discover and activate them. Opt-in should be required for any additional processing, ensuring that user consent is meaningful and deliberate. Interfaces should present these defaults clearly and avoid manipulative design patterns that nudge people toward less private choices. Secure defaults, such as encrypted communications, minimal data sharing, or anonymous participation, create a baseline level of protection for everyone, including those who may not fully understand the complexities of privacy management. User control is one of the defining features of privacy by design. This means that individuals should not only be informed about how their data is used, but also have the ability to make meaningful choices. Mechanisms for consent should be straightforward, avoiding hidden clauses or confusing language. Just as importantly, users must be able to withdraw permissions easily and without penalty, ensuring that consent is an ongoing process rather than a one-time checkbox. Transparency in data access allows individuals to see what information is being held about them, while rights to portability and deletion ensure they can take their data elsewhere or remove it entirely. Together, these measures respect the autonomy of users and reinforce the principle that privacy belongs to the individual, not the organization. Embedding data protection into the design of AI systems is not just a legal expectation, but also a technical necessity. This involves implementing encryption to secure sensitive data, enforcing strong access controls, and applying anonymization techniques where feasible. Secure pipelines should be built to protect data throughout its lifecycle, from initial collection to long-term storage. Documenting these measures ensures accountability and provides evidence for auditors or regulators. By treating protection as a design requirement rather than an afterthought, organizations reduce the risk of breaches, misuse, or accidental exposure. In practice, this design-oriented mindset helps make security and privacy inseparable in responsible AI development. Lifecycle integration of privacy by design ensures that protections are not confined to one stage of system development, but are woven throughout the entire process. During data collection, safeguards must be applied to prevent overreach. Training and deployment should carry those principles forward, embedding privacy into models and pipelines. In production, monitoring ensures that safeguards remain intact, catching drift or changes in data use over time. Even at decommissioning, privacy protections matter, requiring systems to securely archive or delete data as needed. This end-to-end integration reinforces the message that privacy is not a static feature but an ongoing responsibility. Technical enablers are increasingly making privacy by design feasible even in complex AI systems. Differential privacy, for example, introduces statistical noise to protect individual records while preserving aggregate insights. Federated learning allows models to be trained locally on devices, keeping raw data out of central servers. Secure multi-party computation enables multiple parties to analyze shared data without exposing it directly, while homomorphic encryption holds the promise of computing on encrypted data without decryption. Each of these approaches reduces the risks of exposure while still allowing organizations to harness data responsibly. They represent the cutting edge of privacy innovation, offering practical tools to turn principle into practice. Organizational responsibilities are equally important in operationalizing privacy by design. Appointing privacy officers or leads ensures that accountability is clearly assigned. Staff training helps spread awareness of principles throughout the organization, preventing privacy from being confined to a small group of specialists. Governance structures should be established to oversee compliance, and resources must be allocated to make safeguards practical rather than aspirational. Without organizational support, even the most sophisticated technical measures will struggle to be implemented effectively. Privacy by design succeeds only when leadership, culture, and technical practice all align. Yet, challenges in practice remain. Balancing the drive for innovation with the need to follow strict privacy rules can create friction. Implementing advanced safeguards like homomorphic encryption or multi-party computation may be technically complex and resource-intensive. Product teams may resist constraints that they perceive as slowing development. Commercial interests can also conflict with privacy goals, particularly when monetization relies on extensive data collection. These tensions highlight the difficulty of moving from principle to practice, but they also underscore why privacy by design matters. Without proactive safeguards, the temptation to cut corners can easily erode trust and invite regulatory or reputational consequences. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The benefits of privacy by design are both immediate and long-term. At the most fundamental level, it strengthens trust between organizations and their users, signaling that personal information is respected and safeguarded. This trust often translates into greater willingness to engage with services, particularly in sensitive domains like healthcare or finance. Regulatory and litigation risks are also reduced when privacy is built in from the start, since compliance gaps are less likely to emerge. Another often overlooked benefit is improved data quality. When data is collected through meaningful consent, users are more likely to provide accurate and relevant information. Finally, privacy by design can serve as a differentiator in competitive markets, with organizations able to demonstrate responsibility and care as part of their brand identity. Cultural dimensions also play a critical role in making privacy by design successful. It is not enough to treat privacy as a checklist of legal requirements. It must be embedded into organizational values. Fostering respect for privacy means building it into engineering culture, where design teams see privacy safeguards as part of good craftsmanship rather than external burdens. Encouraging open dialogue about risks instead of discouraging or hiding them helps create a healthier culture of accountability. Recognition and rewards for privacy-positive practices reinforce this value system, showing employees that privacy is not only expected but celebrated. Over time, cultural adoption turns privacy from a compliance issue into a shared organizational ethic. Monitoring effectiveness is essential to ensure that privacy by design is not merely aspirational. Regular audits provide a structured way to evaluate whether safeguards are functioning as intended. Metrics can be established for how effectively consent mechanisms are working, how quickly rights requests are fulfilled, and how incident response processes are managed. Benchmarking against peers allows organizations to see where they stand relative to industry standards. These measures create feedback loops that strengthen privacy safeguards and ensure they remain resilient in the face of evolving risks. Monitoring also demonstrates seriousness to regulators, showing that privacy is not simply stated in policies but actively measured and improved. Integration with AI management systems helps align privacy safeguards with broader governance frameworks. Documentation from privacy reviews can be incorporated into system cards, making privacy considerations visible alongside performance and fairness data. Privacy monitoring results can be linked to enterprise risk registers, ensuring that privacy is treated as part of overall organizational risk management. Centralized oversight systems make it easier for leaders to track compliance, allocate resources, and intervene where safeguards are weak. This integration prevents privacy practices from existing in isolation and instead embeds them into the governance structures that guide the entire lifecycle of AI systems. Cross-border implications add another layer of complexity to privacy by design. Legal frameworks vary widely across countries, with some regions mandating strict localization of data, while others permit international transfers under certain conditions. Federated models may help navigate conflicts by keeping data local, while still contributing to global model training, but they bring technical and operational challenges. International transfer mechanisms, such as standard contractual clauses, may be required for compliance, though uncertainty remains in some jurisdictions about their adequacy. Organizations working globally must account for these differences, recognizing that privacy by design means tailoring safeguards to meet diverse and sometimes conflicting legal standards. Scalability considerations also shape how privacy by design is implemented. Startups may face challenges in dedicating resources to privacy engineering, while large firms must coordinate practices across sprawling systems and teams. Automation offers partial solutions, particularly for managing consent and access rights at scale. Standardized templates for privacy policies and safeguards can reduce workload and improve consistency. Ultimately, resource allocation is crucial. Privacy by design cannot be sustained if teams are underfunded or overstretched. Scaling effectively requires both technical tools and organizational commitment to ensure that privacy principles are upheld across different sizes and types of enterprises. Future developments suggest that privacy by design will become even more deeply integrated into AI regulation and practice. Policymakers are moving toward explicit requirements, with forthcoming laws expected to mandate privacy features as standard rather than optional. Generative models, which often handle sensitive prompts and outputs, will face increasing scrutiny for how they collect, process, and store personal data. Technical toolkits are expanding rapidly, making advanced protections like differential privacy and secure computation more accessible to practitioners. At the same time, the growing demand for certified privacy engineers highlights the need for professionals who can translate principles into practical safeguards. These developments point to a future where privacy by design is not only best practice but also a professionalized and regulated standard. From a practical standpoint, several takeaways are clear. Privacy by design must be embedded throughout the lifecycle of AI systems, from the earliest design discussions to decommissioning. Achieving this requires a blend of legal compliance, technical implementation, and cultural commitment. The benefits: trust, compliance, data quality, and differentiation far outweigh the challenges when principles are consistently applied. At the same time, integration with governance structures ensures that privacy safeguards are not isolated but part of a holistic accountability framework. Organizations that take a proactive stance will be more resilient in the face of both regulatory scrutiny and public expectations. Looking to the future, privacy by design will likely become a universal expectation, with more explicit regulatory mandates shaping industry practices. Global convergence of standards is expected, although some regional differences will remain. Automation will play a growing role, enabling organizations to manage consent, access rights, and monitoring at scale. Emerging AI modalities, such as multimodal and real-time adaptive systems, will expand the scope of privacy challenges, requiring novel adaptations of established principles. The overall trajectory points toward deeper integration, where privacy by design is woven seamlessly into both the technical and organizational fabric of AI systems. The summary of key points reinforces the importance of grounding AI practices in privacy. Core principles include minimization of data collection, purpose limitation, and strong default protections. Lifecycle integration ensures that safeguards are not isolated but span collection, training, deployment, monitoring, and decommissioning. Technical enablers like encryption, federated learning, and differential privacy offer concrete ways to operationalize principles. Cultural and organizational factors are equally critical, as privacy thrives only when it is treated as both a technical and ethical priority. Proactive adoption of privacy by design strengthens resilience, ensuring systems are prepared for both scrutiny and evolving risks. In conclusion, privacy by design represents a proactive safeguard against the misuse and overreach of data in AI systems. By embedding protections at every stage, organizations demonstrate respect for individual rights and compliance with legal obligations while building trust with stakeholders. Integrating organizational accountability with technical safeguards creates robust systems capable of withstanding regulatory, ethical, and practical challenges. The benefits are clear: stronger trust, reduced risks, and a reputation for responsibility. This discussion naturally leads to the next topic: differential privacy, where mathematical techniques provide a powerful way to preserve individual anonymity while still enabling meaningful insights at scale. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.